Last thing I want to talk about is something that we started playing with, and I think this has also a lot of legs. Matter of fact, I'm reviewing a paper right now which did what I predicted that should be done last year, and I'll talk about it, although I don't feel comfortable putting the data up. All right, this is a graduate student that worked with us out of EPFL, École Polytechnique Fédérale Lausanne, Switzerland, and Charlotte Lekiefer. And Charlotte's a whiz with the nanosims and with transmission electron microscopy. And she came out and worked with us out on Catalina. And the question she wanted to ask was, how does carbon and nitrogen flow through a symbiotic system? And the idea is that during the day, the symbiotic dinoflagellates are sitting on the spines, okay? So you see these individual dinoflagellates. And then at night, they migrate down and are vacuolarized inside the foraminifera cytoplasm, which is inside the shell. This is a diurnal migration. Every morning, the symbiotes come out. Every night, they go in, okay? And of course, during the day, when they're out on the spines, they're photosynthesizing. We know this from a lot of evidence that we have from experiments that have been conducted in the past. Now, the symbionts themselves are dinoflagellates. If you ever look at a TEM of dinoflagellates, they're immediately obvious. You can show me 10 TEM images and I'll go dinoflagellate, dinoflagellate, dinoflagellate. And the reason is because they're the only group of organisms that have condensed chromosomes during their entire life cycle. Okay? All other organisms, once a cell divides during mitosis, the chromosomes then disperse and you basically have chromatin. You just can't visualize the chromosomes in the nucleus. With dinoflagellates, you can. Each of these is a chromosome. Now, here's your chloroplast around the periphery. You can see these parallel thylakoids. And then on dinoflagellates, and the particular species associated with these foraminifera, they have this sort of ball-like structure that comes off the chloroplast called a pyrenoid. All right, so you see a close-up over here. Thylakoids go into it. And then this is where starch accumulates in the cell. So as photosynthesis occurs, it produces starch, and that starch is accumulated within the cell. Now, I have never taken a time-lapse series. When Charlotte produced some of the images I'm going to show you, it just knocked my socks off. All right, so we're dealing with pyrenoids. Here's our starch. And what Charlotte did was she came in and she worked with a double label, okay? She basically added C13 DIC to the water. So we basically the water was 50% carbon-13, really heavy carbon-13 spike. And we did another series of experiments and we doubled up the experiments where we added N15 nitrate, N15 ammonia, and we fed the foraminifera artemia that had been fed on C13 and N15 enriched food. So the food itself was labeled. Okay, so she then had a group of organisms, and at 45 minutes, 2 hours, 6 hours, et cetera, here's the dark period. Okay, she pulled out a couple organisms, fixed them for transmission electron microscopy and for nanosims. So this is an image looking at a TEM image, okay, looking at one of these specimens after 45 minutes in C13. Okay, you can see this. Here's all the chromosomes. These are all the dinoflagellates. And then she went and she took this section, which was sitting on a copper grid, put it in the nanosims, and then scanned it for C13. And what she got was that. And then she overlaid that onto that, and what you wind up with is that. Okay, so you are now looking at the starch sheath sitting around the pyrenoids. Okay, after 45 minutes, you can see the carbon that's accumulated and exactly where it is. And you'll note, by the way, that this C13 is not distributed anywhere else through the cell, nor this is the foraminifera, nor maybe a little bit of spots in here where there might be some vacuoles that have DIC in it, but for the most part, these guys aren't lit up at all. Now, come on. Let's take a look at after 6 hours in the dark. So now we basically move from 6 hours light plus 6 hours dark. Okay, all these guys, those are all your starch granules that have accumulated inside the dinoflagellate. Okay, that hasn't been translocated, it hasn't been moved out. All right, you start to see the foraminifera now is loaded with C13. And this happened after the symbionts went inside the foraminifera. So they're starting to pass on carbon to the foraminifera. Okay? What's really, really cool is if you look at the TEM images, okay, and I have one in the next one, these are lipid droplets over here. And you can see the lipids really lit up over here. So lipids starting to accumulate that's really rich in C13. And the lipid appears to be the first step in the transfer of starch or carbohydrate to the foram. So here's now all these starch granules. You can see them all lit up in C13 space. These are lipid droplets that are right adjacent to the vacuole membrane, and they're all lit up. It looks like, as far as we can tell, that the first step is to provide the foram with carbon in the form of lipid. And you can see up on top, this is the starch delta C13 as a function of time. Okay, it rises and it's dropping off after we hit the dark as it's losing its starch, it's using it. And you can see the lipid rising up through the night as it accumulates. Why lipid? Two reasons. Number one, it's easy to go from a starch, from a carbohydrate to lipid, but the other is forams have a problem in the open ocean. They're making a shell. They're calcifying. Okay? Calcite has a density, it's 2.2 grams per cc. It's like more than twice as dense as water. You add a lot of calcium carbonate, you're going to sink. Okay? There's no other way about it. Every night, these guys produce a ton of lipid, and that counteracts the buoyancy. It provides a buoyancy source to keep the foraminifera up in the water column, okay, and counteract the fact that they're continuously calcifying and adding shell. So this came out of just looking at the carbon story. The nitrogen story knocked my socks off because it looks like foraminifera themselves are able to take up nitrogen from seawater. So what we're looking at here is the top panel. It was a double label experiment. So the top panel is C13 on the nanosims. The bottom is N15. Okay, so here's our TEM images. Up on top, you can see all the starch granules with C13. Here's the nanosim on the right. This is nitrogen, so this is now after 6 hours in N15 nitrate. You can see all these open circles with nothing. It's because it's carbon, it's all starch, there's no nitrogen in there. But you can see the dinoflagellate, which here's our nucleus, is chock full of N15, as is the foraminifera. It's loaded with N15, which means it has the ability to sequester nitrogen from the seawater environment, which makes a lot of sense for an organism that's evolved in an oligotrophic environment where nitrate and phosphate become two of the most important nutrients that you want to keep in the symbiotic system rather than letting it get out into the open ocean to maintain your symbionts and their photosynthetic rates. Okay, so we wind up with nitrate showing up in quite a lot after 6 hours, but it was the ammonia that just blew me away. So here's what ammonia looks like. This is a dinoflagellate, 6 hours also. This was one that's in the cell. So here's our TEM, here's our nanosim in the overlay. So you can see that in nitrogen space on the bottom panel, the nucleus is glowing. Okay, it's just sucking up ammonia and nitrogen and incorporating it into DNA. We have organelles, these organelles in the system that we know are rich in proteins. I think that they're related to biomineralization. They're the proteins that are going to be forming the shell the next day. They are just absolutely loaded. I mean, they're maxed out with respect to N15. Okay, and the entire cytoplasm of the foram is just loaded with N15. So ammonia is just going straight in. It's not escaping this symbiotic association at all. And they have clear organelles that when they have access to nitrogen in the form of ammonium, it's going straight into proteins. Guys, think about this. I mean, we can do this now. This is TEM. Anything you're working with for looking at carbon and nitrogen translocation in organisms with respect to isotopes. Okay, imagine sulfur. I mean, you can do anything with these right now with the nanosims combined with TEM and your experimental situation. This is food. This is carbon-nitrogen labeled food. Carbon on the top, nitrogen on the bottom. You can see the vacuoles. All right, this is like little bits of Artemia that were labeled, and they're glowing, but it's obvious that nitrogen is being moved out into the host after 6 hours, or this is 8 hours after feeding. Okay, so anyway, we're working on this right now. We have more questions than we have answers on this, obviously. We don't have a mechanism for showing how we can get nitrogen into the foram. So one of my colleagues, Joan Bernard, had developed this technique for looking at marine cores, taking sedimentary cores and looking at life position of organisms within a sedimentary core and their interactions using a thing called fluorescently labeled embedded cores, FLEC. Okay, she published this. This was, it was in a book, okay. The idea was that you take a core and you can stain it, okay. You can look at with epifluorescence after you've embedded it in plastic. You can see organisms in, this is a foraminifera in the sediment, okay, and you can do TEM images of the samples themselves. All right, and the thing that I'm reviewing right now is they've taken this and they've done exactly what we did with the planktonic forams in these cores. They've labeled with N15 and C13, and they're looking at N15 and C13 flow within the sediment core and the interactions between different organisms that are in close proximity with one another. There's no reason you can't do this in a freshwater aquatic environment, and with a little bit of thought, you probably can do this in a soil environment also, with labeling with N15 gases or C13 labeled gases, and see where that the uptake is and how the carbon is flowing from one organism group to another. Exciting possibilities on this. I know Jed was talking about something they're doing right now, which if you're interested in this, he might be able to tell you more about it. Okay, so I want to finish this up by just saying that the new instrumentation that's coming online, I think, is going to play a critical role in the next couple of decades of stable isotope and elemental geochemistry. There are too many new questions and types of things you can do at the frontier between these different techniques. And laser ablation, nanosims, SIMS, TEM, some of them are old, some of them are new, combined with gas source IRMS. Wow, it's an exciting time because it's pretty much now we have the techniques to be able to tackle a lot of the problems that you can think of that nobody's touched, a lot of low-hanging fruit at the moment. Very, very important, okay, very important, okay. Things like SIMS, nanosims, laser ablation are the right tool for the right problem, but the wrong tool for about 90% of the problems. Okay, you just have to keep that in mind. You can't just want to do nanosims or SIMS or laser ablation. There's a lot of time, and in some of the cases it's $1,000 a day on the SIMS. But for the right problem, you can't do it any other way. Okay, so you carefully have to design your experiments if you're thinking about some of these tools. And I think that a lot of the breakthrough, there's going to be a lot of breakthroughs and discoveries made using these types of techniques in combination with what we're already doing now. And, again, this huge wow factor, you just see it in the results of proposals that get submitted and the reviews. And also, I think that you're going to start seeing a lot of universities that are interested in wanting to hire people who are working with next-gen type of instrumentation and problems. And so just keep it in mind. Okay, so finished up with, this is all just finishing up. I'm just saying, I think these technological advances, they got me excited, and I'm going to take my career to the end, and I'm going to be playing with these things. You ought to take a look at them. So that's a good place to stop, and I think, come on, go forward one more. There you go. Thank you very much.